Great, great. So I'm live, so let's get started. Welcome back, everyone. Today we're going to be talking about gradient descent. This is probably kind of the the general form of the most widely used algorithm in like all of data analysis today, if not for like so it's at least one of the top three for all of compute. It's unclear how much is devoted to stuff like crypto, and maybe there's some big weather simulations are not doing this, but like most of kind of data analysis is based on this algorithm. So well, it's pretty important. So we'll go over the basic algorithm today and kind of the most core essential things you need to know about it. Yeah, so that's what's on tap. So let's see. So where are we in the schedule? We are going to talk about gradient descent, the algorithm today. Also about understanding how fast it runs, and this will be a notion of convergence, which if you have not seen these sorts of iterative algorithms before in like a scientific computing class or a different machine learning class, this will probably be new to you. Just conceptualize what that means and give you the basic understanding of when this works and when it does not work. And then the next lecture on Wednesday, we'll be talking about how we then apply this when we actually want to fit how we use gradient descent to fit a model onto data. Okay, and then there's kind of a really clean formulation. We'll see the third algorithm for the linear regression problem. And it'll really give you insight into how this fits how you use gradient descent to fit kind of a model to data. This will come back in the classification section, but then we'll move on to some unsupervised learning after the break. Couple of other notes. Quiz 3 is basically graded. There's one small thing where waiting to do. So sorry, those are not posted yet. They will be posted soon. I will say the scores were a bit lower for quiz 3. All right, so not like drastic, like the whole class is going to fail or anything like that, but like they're a bit lower than the other quizzes. Probably there was less review in this quizz's material, so I want you all to kind of make sure you're studying for the quizzes and preparing well for the cheat sheet you prepare for them, so that I hope the class does better in quiz 4. I don't think the hardness necessarily increased that much, but there's probably less review. So make sure you spend some time doing it. This does constitute a non-trivial fraction of your grade. All right, so over all the quizzes. So each one is not too big, so don't sweat it too much, but kind of make sure you're not just showing up without at least reviewing, making sure you understand the material. There are office hours for the TAs if you want to review, or time with me. You can see this on the website. Okay, so homework 4 has been posted. This homework will be on gradient descent. The first third of the homework will basically be roughly applying the stuff we go over today in class. Okay, so you'll be able to start on that pretty much right away. The first function will be nice. The second function will be hard to work with. You just need to procedurally kind of do it and see what's going on to get kind of the full credit for that question. But I will also give an extra 5 points to any student to do significantly better than the rest of the class. So if you want to try some of the advanced techniques we see today, so it'd be great to explore those. You'll get a better sense of how everything works. The second part will be about applying gradient descent onto data. And you're going to fit a linear regression model with gradient descent. We've kind of broken it down step for step for you. But this will be probably the most challenging assignment you'll have in this class over the semester. So don't wait till the last minute to do this one. it will be less directly building off of exact code that you see earlier in class. You'll have to kind of use what you've learned from those code and what you see in class and put it all together. But it really is kind of the fundamental basics of how you do data, kind of learn models for all of data now. So I think it's really important that you work through this. Homework 4 is not due till after break. Okay, so it's you still have the same amount of non-break days to do it as you normally would, but you also have spring break to work on it. Not saying you have to work over spring break, but I also want to make sure you don't completely wait until the last minute if you have a bunch of other stuff going on. This one might take a little bit longer than the other assignments. Things I think the algorithms will get a little bit more straightforward and built in afterwards, and things will be a bit kind of more straightforward. So this is probably the most, if anything, it's the most time-consuming, tricky part for students who kind of haven't been playing with this sort of stuff before. Great. Okay, so let's get into the lecture today. So we're talking about gradient descent, and I want to start by kind of reviewing the notion of gradients. Let me review it and go through kind of a very quick example as well. And remember, this is a function. The original function goes from RD to R. So that means that if you have an alpha, which are the parameters you're interested in RD, right? So this lower kind of the x-axis is actually in this picture trying to represent a multi-dimensional space. And I can't really draw it on here, but for every value alpha, right, there's some function. Okay, there's some function f, right? The y-axis tells us the value. And what we want to do is go up till we hit the function, and this reports this value f of alpha, right? And then the gradient of the function is written as this nabla upside down triangle f. This is gradient of the function, and this was df d alpha 1, df d alpha 2, right? So it's made up of a bunch of these it's now a function. This is now a function from RD to RD, and it tells us the direction, okay, and the scale and the length of the steepest increase. Okay, that's a little bit hard to draw in this where I compressed all of the RD down to one dimension, but it's some direction which is increasing the most. So, okay, so there's only two directions. It's increasing going to the right. So the arrows point to the right, and the magnitude tells you how fast it's increasing in this direction. Okay, and I can compute this by I only need to compute the partial derivatives with respect to one of the coordinates, the second coordinate, the second value here, all right? So it could be a function going from RD to RD, okay? And so, so it's given me this sense. So this, so I can think of if U is the direction of kind of steepest increase. Okay, so that would be there's a U in this space. And so let's say that U, the norm of U is equal to 1. Then if I take the directional derivative of f of alpha, this is going to be equal to the gradient of f, which is again a vector dot U. Okay, so this will then be the scale, but if
if this is true, then this is going to give me back the norm of this gradient, the length. So then this will be the amount of increase. Okay, the scale of it. Okay, so if I take the directional derivative in the direction of steepest increase, okay, then this is going to give me back, then this implies that u is equal to the normal direction divided by the norm of the normal direction. So it's just a normalized version of this direction of the gradient. Okay, so we're going to use this property. All right, but before we do that, let me go through kind of a simple example. So let's say we have a function here. Okay, so we're gonna say that a is going to be equal to, we'll just say x from notational simplicity. Let me write that alpha 0 equals x, alpha 1 equals y, and alpha 2 is equal to z, and this is in R3. So we're in a three-dimensional setting, and so now we're going to have a function that takes in a value x, y, z, right? This is the three-dimensional, this is our alpha, okay? And so the function, for instance, could be a function that looks like 3x squared. Let's do minus 2y to the third minus 2x e to the power z. Okay, this seems kind of a weird function, but let's just walk through this so you see how this works. Okay, and now we want to understand the gradient of this. And remember, this will be df dx, df dy, df dz. Okay, so the derivative with respect to x, right, is going to be the first coordinate. That's going to be 6x, right? Because I took the derivative of 3x squared, I get 6x, but I also have this other term, minus 2e to the power z, right? So the second term has a y, and no impact to the choice of x. The third term has minus 2e to the z, okay? Now I take the directional derivative with respect to y, okay? So that's going to give me, only the second term matters, is going to be minus 6y squared. And then the directional derivative with respect to z, well, the derivative of e to the z with respect to z is e to the z again, right? So and then I only have to worry about the third term, 2x e to the z, okay? So this is, okay, so I've computed the derivative, right? The derivative goes from R3 to R3, okay? So now it's now a function where the output of the function gives me a three-dimensional vector, okay? So then we can calculate the directional, the gradient at a value, right? Minus 2, 1. So I can set alpha equals 3 minus 2, 1, right? So if I look at a particular point in the space, how the derivative of the gradient at the space in my alpha value for 3 minus 2, 1. How do I calculate this value? Well, then I just plug in these values, right? So x is 3, y is minus 2, z is 1. So I'm going to get, let's see, 18 minus 2 to the e. Okay. Okay, e is a constant here, right? And then for the second coordinate, I just plug in the -2. I'm going to get minus 2 squared, which is 4. So it's -24. And then the third coordinate, I need to plug in x and z, right? So I get a -2 times 3 times each of the 1. So this would be -6e. Okay, so if I evaluate the gradient at any actual location, I'm going to get back a vector. This can no longer be a function anymore. This has to be actual values. I know it's maybe confusing with the e in there, but the e is a constant, right? So it's actual values I get out. This tells me the direction of steepest increase of this function. Okay, so we won't have to, I'm not going to ask you a lot of calculus in this class. Nothing should be hard, but you should understand the form that these things take, right? And on the homework, you'll do a little bit of calculus just as practice, just so you can compute the derivative of functions. Shouldn't be significantly harder than so doing this. Turns out when you apply it for data, we'll kind of know what the derivatives will be when we write down the function. So when we apply it for data, we'll have to do even less calculus than when we actually kind of do it in practice. Okay, so this is clear. This makes sense. The gradient is now a function from RD to RD. I get out kind of three-dimensional vector, and then when I apply it, I get, and that vector is a function. It just still depends on x, y, and z. And this output is an actual vector. Okay. Okay, so how do we use this? Okay, let's go to the gradient descent algorithm. Okay. Gradient descent. Okay, so now we're given as input some function that goes from RD to R, right? So we have RD on the x-axis here, and this is R, the value that we're actually trying to compute. Okay, and the goal, okay, is going to be the minimum choice of alpha in RD of the function value. Okay, so before we solved this, a version of this for when we had points in one dimension, we just took the mean. When we were doing kind of, when we were looking at linear regression, there was a closed form way to solve this. I gave you this linear algebraic expression. But now we're not assuming we have that. We just have a function, and we want to be able to compute the value of alpha star that is minimizing this. This is alpha star here that is minimizing this function. Okay? Okay, so let me write up the general version of this algorithm. So step 0, you need to initialize. So I need to start someplace. I'm going to set this as alpha 0. I'm writing a superscript in parentheses. It doesn't mean I'm taking it to a power, but the subscript, it's a vector, and I don't want you to be confused with the coordinate of that vector. Okay, so this is the 0th step. It's the starting point. This is some alpha starting point, and this is some point in RD, and this is kind of a guess, kind of a guess of where the minimum would be. And it's, you know, I could pick some value. Let's say this is alpha 0, and I could evaluate the function there. So that's my guess, right? Okay, I'm going to guess at where the function is. I'm also going to have some parameter k I'm going to set to 0. Okay. Okay, then the most important part of the function is going to be a simple loop. Okay, I'm just going to have a repeat loop. Okay, and at the repeat, is only going to have one line inside of it. Very simple. I'm going to I'm going to start with the value at k, okay? And I'm going to get a value at k plus 1, okay? So I'm going to
Somehow go from my kth guess of where the minimum is to the k plus 1 guess.
okay? And I'm not just going to sit there. I'm going to use the gradient of alpha, the kth guess of alpha, okay? And the gradient is sitting, say, is a function here that is pointing in the direction which is increasing the most. So it tells me which direction does the function increase the most. So I don't want to go in that direction. I do not want to go in the direction of the gradient. In fact, I want to go in the opposite direction. So I'm going to subtract. I'm going to subtract the gradient, and I'm going to, in fact, subtract it by some coefficient gamma k. Okay, so there's going to be some term here called, this term is called the learning rate. Okay, and in a lot of cases, it's just going to be a constant. Okay, but it could in general, and we'll see throughout the lecture today, that sometimes we want to change it a little bit throughout the algorithm. So on step K, I might want to change this learning rate small amount. Okay, and I'm just going to repeat this step. I'm going to move in the opposite direction of the gradient. That's the direction of steepest descent. If I move in the negative of it by some learning rate. And I'm going to do this until, okay, some condition when I, so when I think I'm done, it could be something like k is equal to some threshold t. Okay, this would be a total number of steps, or maybe more commonly, I would say that if I look at the gradient at step k, and I say this is smaller than some threshold tau. Okay, I say the gradient, it incorporates not only the direction to move, but also how steep is it increasing. And if that steepness is actually really small, it doesn't move very much, then I can say, okay, I'm probably close enough, I can stop. Okay, and then finally, I'm going to return alpha k. Okay, so the last thing I do is I say, once I determine I went either enough steps or my movement is small enough, this would be enough steps. I'm like, I've had it. I've done this loop too many times. I'm going to stop. Or I'm going to say the improvement is going to be small enough. Okay, then I'm just going to stop the algorithm. Okay, so this is, if you haven't seen algorithms like this before, it's kind of a very valid algorithm, but it's not like sorting. I don't like say I'm sorting and at some point I say, okay, it's probably close enough to sort it, I'm going to stop. Right? This would be kind of weird for a sorting algorithm to do this, or maybe for a searching algorithm. Actually, most actual way you run a search is you would probably stop if you think you're close enough, but that's save that for another lecture. But I'm not necessarily going to get to the true optimum. Okay, I'm going to stop when I think I probably got close enough, or I spent enough time. So I've been running this for too long, right? People are worried about, is this algorithm actually going to terminate, right? Is there a stopping condition for the algorithm, or is it an infinite loop? Well, if I put this constraint here, it can't be an infinite loop. After t steps, I'll stop, right? So sometimes you're like, well, I'm going to run it long enough until I think either it's good enough or something may have gone wrong and it's not going to get there for a really, really long time. So I might as well stop here. Okay. Okay, but the algorithm is really, there's really this one piece of code here which really relies on just computing the gradients. If I have the gradient, I basically can iteratively compute it. and evaluate it at different points, right? Remember, I didn't just want to compute the gradient, I need to compute this function once, derive this function once, and then evaluate it at many different points. Okay, so those are two different aspects to it. So I compute, derive that gradient once, and then I can compute it many times over and over again as as I'm getting closer. Okay, let me write down kind of a simple form. Most times you're going to use this version. I'm going to set alpha at 0, 0, 0. If I don't know what to choose, I might as well start at the all zeros. Seems reasonable. That's often a good place to start. Okay, then I'm going to repeat. Alpha is going to be equal to the previous choice of alpha. I don't need to store all the previous choices necessarily. I just kind of store one state and I update the state minus a fixed learning rate times the gradient evaluated at alpha. Okay, so I don't need to store the result after every step. And I do this until the most common way to do this is to have a threshold and say when the gradient decreases below some value, then I can stop. Okay, and then I'm just going to return alpha. Okay, so most of the time you're just going to implement this version of the algorithm. This is kind of outlines a more general version where we can put in some, some bells and whistles here. Okay, computing the gradient is often hard, but that's often automated within the software you're using. If you're using like TensorFlow and doing backpropagation, we'll talk a little bit about this later in the semester. It's going to do that for you. If you don't know how to compute the gradient, it'll do like it's like an autograd that will compute the gradient for you. You just write down the function. So a lot of these things are kind of automated, but you need to really understand the kind of basics of what's going on here if you haven't seen this before. Okay. Okay, before we go any further, I want to, there are a couple of things I need to explain about this. Like, how do we choose the learning rates? This is the big question. Like, how do I know if this worked correctly or not? Right? If I'm sorting, there's like a certificate I can do. Is the list sorted or not at the end? I don't have that certificate. I want to know, did this actually work or did this not work? Okay, and so this is a little bit more complicated to think about here. Okay, so one of the really important tools I want to bring up is that you should try and plot things and use visualization to kind of help verify if you can, okay? And so for the first part of the homework assignment, we're going to work with some two-dimensional functions, and we're going to be able to plot it. And this, I think, will hopefully give you some insight. Okay, so this is linked off of today's lecture on the webpage. We're going to look at a function. The function is going to depend on x and y. It's this, 0.75 x minus 1.5 squared plus y minus 2 squared plus 0.25 xy. Okay, I don't know, some function. I've defined a function here. Okay, it'll be useful inside of a notebook. You can define functions and then call them over and over again. So this will be useful to do. I won't actually need to call the function to run gradient descent. I only need to call its gradient. Here, I've derived what the gradient is, okay? Note that the output here of the gradient is going to give me a NumPy array of length 2, right? Not a single value, but a NumPy array. I calculate the gradient, I calculate df(dx) and df(dy) separately, right? So I'm going to have a function for the gradient. Okay, now before we run gradient descent, let's plot a function, right? So I'm going to plot it as an iso level surface here.
And what this is showing is the different, kind of for different points in this two-dimensional space from 0 to 5 on each axis. I'm plotting all the points that have kind of an isolevel that have the same function value, right? So the minimum is going to be here, and then this will be all these points of the same value, all these points of the same value, and so on, right? And so when the lines are getting closer and closer together, that means that it's getting steeper and steeper. Yeah.
So each rank is basically alpha K.
No, I haven't plotted gradient descent yet. Okay, so I'll plot that. Now I'm just plotting the function value so far.
I'm using this linspace command is giving me 26 points between 0 and 5. So I'm basically just designing a grid, right? And then this mesh grid command allows me to put them all together, and then I evaluate the function everywhere. Okay, and this is just plotting the function. I haven't run gradient descent. And this contours, and this is kind of just a standard built-in way in Python. It's got a lot of cool stuff built into it. Okay. Now we're going to run gradient descent, right? We're going to choose to initialize at 5, 4 for this example. It makes the example work well. Well, I said the learning rate is 0.2, but here I've implemented gradient descent. I initialized at 5, 4. I said I'm going to do 10 iterations, so I'm just the one that counts the number of iterations. And then I'm going to store them inside this array, so I'll be able to plot. Okay? And I'm going to set the learning rate to be, I'm going to take 10 steps, so I know it's going to be a size 10 array. And then I'm going to, the learning rate I'm setting to 1. Okay, so I'm just going to fix the learning rate. Then here's the algorithm. Algorithm is even shorter for stupid pop-up. Okay, so for 1's the number of iterations, so for 10 steps, I'm doing the current value, I'm using V for my alpha here, minus gamma times the gradient. Okay, and I'm going to put them in this array. So it'd be 1 step if I wasn't going to plot stuff, right? So I just ran the algorithm there. I ran the algorithm. Okay, and now let's plot it. So I'm doing my plot again, but now I'm plotting the steps of the algorithm. I'm starting 5. So 5, 4. Let's see, 5, 4 was over here. And it took 1 step in the gradient, it wound up over here. And then it said, well, now the negative steepest ascent is this way. This is the minimum. I'm going to walk towards the minimum, but it went way too far. It's bouncing back and forth here. So this is not good. Okay, so this is not how it's ideally was supposed to run. What's happened is I set the learning rate too high. Okay, it's kind of finicky if I set this learning rate 10 too high or 1.0 too high. Okay, this was too high. So let's set this smaller, 0.1. Okay, let's set smaller, see what happens. I reran the algorithm and let me plot again. Okay, so now I started at 5, 4 up in the same spot in the right corner. Now it didn't jump outside of the area I'm plotting. That's good. And it's making these steps going down, 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 but I'm not getting all the way here to the minimum. Okay, so now the learning rate's too low, right? You know, so I feel like Goldilocks, right? Papa's porridge is too hot, Mama's was too cold, right? Yeah. We could increase the number of iterations. Yep, let's do that. Let's increase the number of iterations. This is a very reasonable thing to do. Increase the number of iterations. And, oh, still didn't make it. Okay, so the minimum is probably here, but I still didn't quite make it. Okay, so if I increase them to like 100, it's probably going to make it, right? Let's do it. Okay, if I went to 100 steps, it made it, but I think I can make it there in fewer steps. Okay, so it's better than jumping all over the place.
Okay, it's definitely better than that. I change it now. Okay. Show. Uh-oh. Okay. So let's try. Sometimes on iPad, not the best. Let's try 0.5 with only 10 steps. 0.5.
Okay, so 0.5, I got there in only 10 steps, probably only like 7 or 8. But this one was kind of dangerous. I feel like I almost overshot. Right?
What you kind of like to see would be something more like 0.2. Let's say 2.5 here and run this. Oh, let's do, that was almost too lucky. Let me run 0.2. All right, so if I do 0.2, I'm getting pretty close in 10 steps. Maybe I need to run for 20 steps. So I probably would have been good with let's do 20 steps at 0.2. I forgot to rerun the algorithm. Okay. No, I don't think I ran this correct. Okay. Got to rerun every step, otherwise. Okay. No. Oh, if I run it. Okay. Okay.
So I do 20 steps at 0.2. I'm pretty happy with it. It's getting there. It may not be exactly to the minimum. In fact, it almost can't be exactly to the minimum, but it's getting quite close. Okay.
All right. So this is the sort of plot you kind of want to see, something like this, where it's kind of not overshooting and is able to get there in not too many steps. Yeah, yeah. So, okay. So you'll do this for your homework. You'll play with this. I'll give you some learning rates to use and you'll try them and just see how it works. And then I'll give you one of the functions I'll give you is not going to look so nice. And the initial thing you run is not going to work as well as you want, but you can try some other stuff to see what happens. Okay. Okay. So what more can we say about this? What we're going to want is that there are a bunch of stuff that can go wrong here. Okay, so we could be in a situation where my function, and at some point you'll design functions that will kind of look like this. Okay, so imagine this was the function here. If I'm over on this side, right, if this is my alpha, then I'm probably going to move, this is alpha 1, this is alpha 2. I'm probably going to move about as I expect. But if I wind up over here, right, if I end up as alpha 7 or 7 over here someplace, well, what's weird is that now the gradient is going to look something like this. Okay, so the gradient is going to be the size of the gradient. Yeah, so this is now. Okay, the magnitude of the gradient is going to be constant on the left side, but it's getting smaller as getting closer to the minimum over here. In fact, it should, if I'm actually at the minimum, this value should be basically 0. Okay, if I'm at the minimum, then the gradient, the first derivative everywhere should be 0. This is a property of the minimum. Okay, but on the left-hand side, I don't see that, right? So this is in a case where the gradient is not is not continuous. Okay, so the gradient f is not continuous, and this is going to be a hard case. If it's not continuous on the left here, this is going to be bad. Okay, I'm not going to be able to say much about gradient descent, because if I'm on the left, my only guide of how close I am to the minimum is the gradient. On the right, this is going to be fine. I'm kind of approaching it for a nice landing. And on the left, it's like, I don't know, I'm going to keep going at the right rate until I get there, but I might overshoot. Okay, so this is a tough case. The other case that I don't want to have, okay, is that if I have a function that looks like this. Okay, so if this is my function, okay, I've got a well-defined minimum here. Okay, but the problem is that between 2 points P and Q, it's not going to be convex. So this is not convex. So what's going to happen is I'm going to start by going down here, and things might be good, and I might say, okay, I'm gonna stop. I'm gonna say that the norm of my gradient is below a threshold, but I haven't yet reached kind of this drop-off point where it starts going sharping. Okay, so if I use this as a guide, that my norm of my gradient has gone small, and that happens as I get close to minimum, well, that could happen when I'm still far away from the minimum. So this is one reason why we don't want this non-convexity, even though there's a well-defined minimum. I will eventually get there, but I might stop too soon. Okay. The other thing we know is if we have a convex function, it's always going to look like this, where everything, there's a single minimum, and it's always going down in the smooth ways, right? So if it's convex, it's going to look nice like this. If it's not convex, I could have this issue. And if the derivative is not always well defined, like at the minimum point here, or it's discontinuous, some weird stuff can happen. Okay. So the question is, when can we say this will work? So if it is convex, I will eventually get to minimum if the learning rate is not too high. Okay, so if the learning rate is too high, I could jump all over the place, right? So if it's convex and I get the learning rate right, okay, so how do I choose the learning rate? Well, okay, so what I want is that here, let me say the learning rate in order to do this, I'm going to consider define something called an L-Lipschitz function. Okay, an L-Lipschitz function, and I'm going to define this generally for a function from RD to RD, let's say. And so we're going to think of the function here, and it's going to be, and we're going to call this function g because it's going to be the gradient of f is when we're going to apply it. So I'll just call this a function g. Okay, and so for the function g, it's L-Lipschitz function if for all p and q in Rd, then I'm going to have the property that I look at the function value between g of p and g of q, and I look at the difference between those function values. Okay, so now the y-axis is also Rd, and I'm applying this at a point P and a point Q. And so I'm getting function values here, and I'm saying how different are these? Remember, the norm gives me a sense of a difference between these, but it extends to the vectors instead. But you can just think about how different are these function values. And I want to have the property that these are less than L, which is this Lipschitz parameter, right? So L is the Lipschitz parameter here. And this is less than P minus Q. Okay, so as P and Q get further apart, the function values are allowed to get further apart. But if I change P and Q by a small amount and the function values change by a large amount, then this is kind of bad. Okay, so that could be happening in this region here. Think of the slope. If the slope is ever very high, the maximum slope of the function is kind of determining this value out. It's how high can the slope be anywhere on the function. And I want to apply this on the gradient. I don't want the gradient to change too quickly. Okay, this example had the gradient change very quickly. It's discontinuous. It's very high, and then it goes to 0. This is a bad case. Okay, this is not L-Lipschitz function for the gradient here. Okay, so I wanted, so the gradient cannot change too quickly anywhere. So okay, so now I can say, so if G equals delta F is L L-Lipschitz, so there's some value L, and I'm going to set the learning rate gamma to be less than 1 over L. Okay, so as the learning rate gets, as the Lipschitz value gets higher, the gradient can change faster. I need to set the learning rate to be smaller. Okay, the safe learning rate is smaller. Okay, if this is true, then gradient descent if I run gradient descent on F, it will converge to a stationary point. Okay, what is a stationary point? It can be a minimum or it can be a saddle point. Okay, and so it might get stuck in a saddle point or like a local minimum. But if F is also convex, then the only stationary point is the global minimum. Okay, then it will converge to the global min. Okay, so if it has some bound on the Lipschitz function, and I set the learning rate low enough with respect to that, it will converge, guaranteed to converge to the global minimum. Okay, and I can say more, that if I run for k equals some constant over epsilon steps, then I can say f of alpha k minus f of alpha star, which is the optimal, is going to be less than epsilon. Okay, so there's this epsilon parameter, and it's 1 over the number of steps.
So if I want to get within like 0.1, I need to run on the order of 10 steps. If I want to get within 0.01, I need to run on the order of 100 steps. Okay, C is a constant. It's kind of a little bit murky.
What exactly this means. This is some sort of constant. Okay, it's a constant. It depends on like where you start. It depends a little bit on how far you are below the learning rate. It may also depend on other properties of like the convexity of the function. Mostly where you start and how far you are below the learning. How far the learning rate is below 1 over L. So I want to be as close to 1 over L as I can be. Okay, and I want to start as close to the minimum as possible. Okay, but if I don't start too far from the minimum, I assume it's within reason, and I don't set the learning rate too small, well then this should work. Okay, so sometimes I don't know what the learning rate is, so I try with multiple learning rates and I see which one gives me the best answer. If I set it too large, I'm going to jump all over the place. If I set it too small, I'm not going to make very much progress when we started. And you can kind of track these things and kind of see like how to set the learning rate. And in practice, if you're doing this on your own and writing it yourself, you'll probably just try a number of learning rates. I'll give you a formula for how to adjust the learning rate in a bit. In practice, a lot of algorithms use these dynamic ways of adjusting the learning rate under the hood. But if you're like the things that you would actually implement, they implement this and they adjust learning rates kind of automatically. And the starting point will be what I tell you a bit kind of later so in the lecture. Okay, but if you're not sure, just try it with different values and kind of see which one works the best. Okay, if most cases, it's pretty fast to run unless computing the gradient is very slow. Okay, so this kind of tells me something, but I'm going to tell you, I'm not satisfied with this fact. I want to get within some epsilon of the optimal solution. I would like to do that, but this many steps is too many. This is the bad bound. Okay, I can do much better than this as it turns out. Okay, this is kind of a conservative bound, and I want to be able to do something much better. And in fact, for solving the linear regression problem, we'll be able to do much better. This would be called like an exponential rate, and we can do a linear rate of convergence that'll be exponentially faster. Okay, so to do that, we have to assume something else about the function. We need to assume what's called strongly convex functions. Okay, so this will be, I'm going to need something like the Lipschitz bound, but kind of on the other side. Okay, so I'm going to say, so F R RD to R is going to be eta strongly convex if, okay, for all alpha and P in RD, okay, so I'm going to have a function right, a function, and I'm going to think I'm at a point alpha, and I want to evaluate it at a point P, say as if I'm moving from alpha to P, right? So how well is this going to work? And I'll try and so I need to satisfy certain condition. I need the property that f of P is going to be greater or equal than, okay, f of alpha, okay, so we plus a how about I write this down and then I'll try and explain it. The gradient dot product with P minus alpha plus eta over 2 of P minus alpha squared. The difference between P minus alpha squared. Okay, this is eta. This is the parameter that is governing this. Okay, so let me draw a bigger picture here. Okay, so we have a function. Okay, this is our function f. Okay, and we're going to evaluate this at some value alpha. Okay, and at some value, probably at some value p. A little bit higher value p. Okay, and now, so we can, the first thing we can observe is f of alpha, this point right here. This is f of alpha. Okay, so it's going to be greater than something, but it's starting there. And then let me look at this term. This term is going to be a linear approximation. It's a dot product with P minus alpha, right? This is P minus alpha here. Okay, so that's in the direction, like P disappeared somehow. Okay, in the direction towards P. So I'm going to move in this direction, right? In this direction from alpha to P, and I'm going to increase with the dot product. That dot product is describing a linear equation. So I'm getting a line through here, and it's deviating from this value f of alpha, so it's the tangent line. Turns out this will be the tangent line because this is the gradient at this point, the direction of steepest ascent, and I'm getting a linear approximation. So I'm going to say I'm doing better than the true value f of alpha plus a linear approximation. Okay, and then there's a third term here. The third term is going to say I'm going to be above this third term here. This third term is going to be a quadratic term. Okay, so it's going to be above a quadratic term. And so let me see if I can draw this. This quadratic term is going to come like this. Okay, so it's going to be a parabola, right? Every quadratic term is going to be a parabola. And so this function, this is f of alpha. So I'm starting at that point, plus the linear approximation, P minus alpha, the dot product. That's the linear approximation plus the quadratic approximation, P minus alpha, the distance squared. Okay, so I'm saying it's going to sit above a parabola. Okay, so, and this eta needs to hold for all points on the green function. So it means I can always put a parabola underneath the green function that is tangent to it. I can make a tangent parabola everywhere. And the curvature of the parabola, how fast it's curving is going to be controlled by the eta. The 1/2 is there. It's always confusing to me. Why is it eta over 2? Well, when I write this down, I'm going to take the derivative of it, and the square is going to cancel out the 1/2. Okay, when I take the derivative. Okay. Okay, I want to put this in contrast with another parabola. Okay, so this parabola here, this one corresponds with f of alpha plus the linear approximation at the tangent. Okay, plus L over 2 p minus alpha squared. Okay, so this term is the Lipschitz property.
This was the one I needed for it to be L-Lipschitz, the gradient to be L-Lipschitz. This controlled it from increasing too fast. I didn't want the gradient to increase too fast. Okay, so I said, I want to be able to, in fact, I want to be able to sandwich my green function in between two parabolas, one that says it's never curving too fast, and one saying it's never increasing, changing too fast. Okay. And so if I can sandwich it between these two parabolas with L and eta, okay, then I can say something very even stronger about it. Okay, so this tells me that's L, that is L Lipschitz. Okay, so if I have both of these together, okay, so if D of F is L Lipschitz, okay, and F is eta strongly convex, okay, so if I can always fit a parabola underneath it, it's always going to be convex, so it's going to be eta strongly convex. Then if I can set the learning rate less than 2 over L plus, plus eta. So I take the average of L and eta, okay, and then I do 1 over that, right? It's 1 over the average of L and eta. So those two parabolas which always sandwich it. Then after k equals c times log of 1 over epsilon steps, I can guarantee that alpha, the value of the function at alpha k minus alpha, the second term is always smaller, right? Then this is going to be less than epsilon. Okay, so and this property, getting this property is called linear convergence. And so I'm saying that in a logarithmic number of steps, I'm getting epsilon close. This is really great. So it means they converge very, very quickly here. Okay, so this is much faster than before. To get kind of, I'm thinking I'm getting roughly 1 digit of precision every constant number of steps. For every, the constant depends on C roughly, depends on whatever C is. I'm getting 1 digit of precision for every constant number of steps. I take 3 steps, I get a digit of precision in the optimal value of the function. So this is really great. This means it's converging super, super fast. There are some things where you can get kind of, you can get like a log number of steps, but it's like there are some settings where you can get that, but usually not in data analysis. This is really what you hope for. This means that even though it's an iterative algorithm, it doesn't ever quite get there. After a really small number of steps, if I set the learning rate correctly, I'm getting very, very close. Okay, and so I shouldn't really worry. And if, as we'll see, like the function I'm getting is not going to be perfect. The function is going to be an approximation of the true thing. So as long as I get like relatively close, I should be kind of pretty happy here. Okay, so this is, I want these nice strongly convex functions, and the strongly convex means they look kind of like parabolas. Okay, what sort of functions have we looked at so far that look like parabolas? Basically parabolas. When we are talking about linear regression, or we're deriving the kind of, the Bayesian inference from normal noise, we eventually derive something like a sum of squared errors, right?
that because we're squaring the errors, we're kind of writing down parabolas. And so this almost has to be a parabola. The function we're minimizing almost has to be some sort of like, has to be some sort of quadratic function. So if we're minimizing some sort of quadratic function, it's going to work really, really fast. Has to be the strongly convex condition. And so one of the things about data analysis is like if in math, when you're thinking about gradient descent, when will it work, when will it not work, you have to worry about all these weird sort of conditions. We get to design the algorithms in data analysis, and we can design the algorithms and the modeling so that our functions are nice. I want my function to look like the strongly convex function, so it always looks like parabolas. If it always looks like parabolas, I know the gradient descent is going to work super fast. Okay? And if I add something that's not a parabola, I should not expect my gradient descent to work as fast. It's just kind of the property. It should be, it might still be Lipschitz bounded, and then I will get something, but might need to take more steps because I may not really be able to kind of understand like how fast I'm getting there and be able to adjust the learning rate, the learning rate to the right values. All right, I think there are, okay, so I want to, great. So I've got about 10 minutes left. I want to tell you how to auto adjust the learning rate. Okay, and remember, I want to write down the core part of the algorithm here is my parameter minus the parameter times the learning rate at step K times the gradient evaluated at alpha K. Okay, so if you remember, if I have a parabola as I'm getting my alpha closer to the minimum, I'm talking about how steep is the function. Think of that's what the scale of this is a direction and a scale. The scale of it is going to decrease as I get closer to the minimum because the function is going to get less steep with the parabola. As I get closer to the bottom, it's become flatter. And so I'm going to take smaller and smaller steps, right? Remember in this picture, as this was a quadratic function. As I got closer to the minimum, then I'm taking smaller and smaller steps and I did not adjust the learning rate here. Okay, it automatically takes smaller and smaller steps as it gets closer to the minimum because the function's getting flatter. And so I know I'm getting closer, I'm kind of honing in on the right solution. Okay, but how do I automatically adjust the learning rate? There are going to be two approaches here. One is called line search, okay? And so I'm going to, at step K, I'm going to choose gamma. So f of alpha K minus gamma alpha K is as small as possible. Okay, so why does this make sense? Can I just, in the one-dimensional picture, it says, well, it looks like I can just take the minimum. Okay, but what's actually happening is I'm going to get these iso lines, right, like I was drawing before, and I'm going to get some alpha here, and my gradient my negative gradient, this is the negative of alpha, is going to be pointing in this direction. It's not pointing towards the minimum. It's not pointing here. This descent is this direction, right? Because think I'm on like a valley. I'm on and I'm going to be pointing down, but not towards the minimum. So then I want to think of there's a line through here, and I want to choose. This is alpha minus times gamma. This is the gamma I want to choose. The one that will get me along this line through the grade direction is the minimum. Okay, so it's kind of like when I chose gamma equals 0.5, it took a really big jump. That was close to the minimum. That kind of got lucky. And then it can turn the corner and go along the bottom of the valley. Okay, but this takes extra work. I have to figure out how to choose gamma that minimizes this. And so typically what you would do is I would choose, well, I would probably not go backwards, but I would choose a bunch of values of gamma and just evaluate them all and choose the one which is the best. And maybe I just choose like 5 or 10 and choose whichever one is the best. There's more sophisticated ways you can do this, but this is a pretty good first gradient descent on this line itself, if I wanted to. Okay. But so I can just try a bunch and choose one, and then, okay. The other way of doing it would be called, so backtracking. And so what I'm going to do is I'm going to start with gamma probably too large. Okay, and then I'm going to repeatedly set gamma equals to beta times gamma, where beta is something like 0.75. So every time I multiply it by beta, I'm decreasing it by a factor of 3/4. Okay, I'm gradually shrinking it. And once I think, and I shrink it if I think something is going wrong. I'm jumping way too far and the function value increases. Okay, so I shrink if I get the following expression. If the function value f of alpha gamma, this is my current guess of gamma of alpha. Okay, so if I evaluate where I think I'm going to go, if this is larger than alpha of alpha minus some my guess of gamma okay, so if you remember the strongly convex property that we wanted, it kind of had to do with I fit a parabola and there was this eta and L, and I needed gamma to be sandwiched in between them. So I'm going to say, let's assume that I had this function, which is parabolic, okay? And I'm guessing that there was some parabolic function here. Okay, and so I'm going to guess that it's this function here. I don't know what the real function is, but this is my guess of f of alpha minus gamma over 2 . Okay, so I think if I move in the direction of P, right? So that's some direction. I'm moving in the direction of the negative gradient. I kind of expect to be decreasing at a certain rate, but that to kind of level off. That's kind of, I'm fitting, this is my guess of what the parabola looks like. I don't know what the true function is. I don't know, but this is my guess of it. And I'm going to compare it to if I did a linear approximation. Okay, so if I'm evaluating, if I'm evaluating here, this point, this is alpha minus right? So that's what this point is here. Then the purple curve is then what's happening is the purple curve,
which is what I'm actually, my function value further here, which is a linear approximation, is dominating the quadratic approximation. Okay, so when I actually evaluated the function,
the point is I actually evaluated the function and the function value was too big. So if the function value is way too big compared to some approximation I have of it, that means that, okay, I jumped too far. I need to decrease the learning rate. That's the gist of it. I'm worried I don't quite have the expression right here, but there's if you look this up in the book, it should be right. I will correct this on the slides if this is wrong, but I'm not sure I've got the picture right here. But if I jump too far and I end up being, my function evaluation at this point is way bigger than I would expect, okay, then this is the sign that I jumped too far, my learning rate is too high, and so I should decrease the learning rate. So then I shrink it by a constant factor, I try jumping again. If my function value is not too high, I probably have it right, so I slowly decrease it till it's within a constant factor of the right learning rate, and then I get the linear convergence, and things go really fast. So you can basically do this if I know I have a strongly convex function, I can start with the learning rate a bit too high, and then I want to get just below the optimal learning rate, and then I will converge very quickly. Okay, and so I'm worried I've got the wrong equation written up here, but there's some tests like this you can do to adjust to adjust the learning rate. So, okay, great. So this is kind of super important kind of so gradient descent is kind of the central algorithm in machine learning. You will get to work on this in your homework. The first part is going to be kind of just playing with the functions I gave you. For F2, you're going to have to kind of think a little bit harder. If you're going to plot them, you may need to adjust the parameters a little bit to plot it, and it may be tricky to adjust things. But you can get full points just by running it. And then we'll see how to do step 2 on Wednesday's lecture, where we see how to apply this on the actual data. Then we'll design the functions F, which will fit our model to the data. Okay, great. We'll stop here.